Okay, guys, again, how we get started. Questions about the syllabus? Any questions about procedural matters working to the course? Questions about the syllabus? Everybody good to go with the syllabus? Questions about guidelines, guidelines for notebooks, guidelines for reports, any other information? Tuesday lab will be upstairs for check-in, instructions in the lab manual, instructions and requirements. Anytime I say instructions, also requirements, then we'll come downstairs and have a little lecture time after we get checked in. I see a phenol. Anything else before we get started?
Is that an aniline?
I see a phenol. Aniline, yes. What type of group is that there?
That's a methyl.
Methyl, one carbon fragment group, not methane, but YL, methyl, ethyl, propyl. Yeah, but the methyl carbon is carbon 11. Okay, that had to be, this time that had to be made. First, carbon 11 had to be made. Okay, how would you make it, etc. But yes, it's called an N-methyl aniline. You don't really have to know that aniline would work. On to the aromatic ring. Aniline and phenol, this sort of have different names. How many lone pairs in this compound? On the nitrogen? One, standard bonding for nitrogen, one lone pair, 3 bonds. Okay, you see the lone pairs here? You got to know they're there. The lone pair of the nitrogen, what type of orbital is it in? You'd be able to answer that question. Hopefully we'll be able to do that today. What type of orbital? How many pi electrons in that compound? Well, it is a pi electron. We have our outline. It's green. Functional groups, okay? Functional groups are your building blocks for making compounds. You want to put together a compound from a structure, you have building blocks to use, functional groups. Put together a structure, C7, H6O2. Okay, put together a structure. Well, you can link every carbon together. We did some very systematically. Those were small structures. Bigger structures, you want to think more just functional groups. Quick building blocks. How many GUS in this formula? Okay? I think it's very important. That's why I teach it to you and tell you it's very important. How many GUS? Looks like 5. Okay. 5 GUS with at least 6 carbons. Hey, we could just put a benzene ring on the board, yeah? More than benzene, because that's just C6H6. 2 oxygens. Do you know a functional group that has 2 oxygens? No, it does, but it doesn't have there's no sulfur in the molecule in the formula, so it can't be a sulfonamide. Carboxylic acid. Let's hook on a carboxylic acid, and that is now C7. Everybody agrees? 6, 7, O2. And I'll bet you a steak dinner it's the right number of H's. How do I know that? Because it's got 5 DUS. And that's going to tell you how many H's are there, so you can go the other way. Okay? Everybody count? It's got 6 H's. There's 5 on the ring, and there's 1 on the carboxylic acid. There you go. And so you don't have to just put every carbon together at one at a time. You know functional groups, you know some workings, right? Okay? A little bit of advice. You like advice? Okay, let's get going. Let's move into hybridization and geometry. Methane. I was told that if we erased with a rag, it would erase better. That's good advice. Methane. All right, you've got the outline there. I'm looking at it. We drew methane on the board before, but we drew it probably, I don't know if we drew it or not, but like this, yeah?
Yes.
All right? But that's not a complete view of the bonds there. What's the bond geometry, et cetera? What hybridization do we expect? So we need to talk about stuff like that, and I'll go through it fairly systematically, so we know how to have a thought process, looking at what we need to look at, answering certain questions. Okay? Ultimately, this is, and we can just sort of start, this is methane, and the carbon is indeed sp3. But how do we know that, etc.? One thing to know about this, okay, is all four of these bonds are identical. Does that seem reasonable? Just looking at the structure. But it's also reasonable based on data. Various data, okay? I'm not just telling you because of how. Many statements are based on data like X-ray crystallography, etc. But it's not only have four identical bonds. But let's think about that. How do we get four identical bonds? What's the ground state configuration for carbon? We drew this before, right? Let's just do the valence shell, okay? We had one ground state configuration of carbon. We did this last time, just valence. The one S is there. We're going to ignore that. Okay. How many electrons does carbon need to fill its outer shell, the second shell? 4. Where are you going to put them at? Well, how are you going to make bonds? Bond is pairing up. We could come in here and bring in an electron maybe from an H and pair up with that one and make a bond in that orbital, kind of. Do it here. What do we do with this orbital?
You fill it before you fill the other two. Well, you have to,
I've already placed it. I feel this before I move up.
but you have to put one in that orbital first too.
I would put one from what? An H or something that it bonded to?
And then you start filling.
Okay, and then I would do what? Then come back and put...
Yeah.
So you're proposing this. And I'm going to end up with what looks like two bonds. A bond is an electron shared from each atom, each nucleus. Two bonds, and this looks like a lone pair. That's just two electrons. Is that a bond or is that a lone pair? To me, it looks like a lone pair. It looks like two bonds and two lone pairs. But we don't have two bonds and two lone pairs. We have four identical bonds. In the end, ground state does not work for us. Okay? No good. All right? No good. Save an ink up here. You can do it. All right? Instead, we get hybridized. And see, that's why I asked you the other day, what's ground state really good for? I don't know. All right? It's a starting point. In organic chemistry, just about everything is hybridized. The orbitals, when bonding occurs, they're more mixed. Okay? Hybridized is just a fancy word for mixing. And it's sp3 in this case. How do you get to sp3? We start with a question. Somebody said, how many electron regions or electron domains around this carbon? 4. 4 regions are best spread out. How? The electrons repel each other unless they don't. They're bonding, but usually they repel each other. They want to spread out the maximum amount. Are my arms the most spread out right here? Or like that? Like that, right? And we're spread out. How do you spread 4 arms out? If I brought 4 balloons together and tied them together, how would they spread out? I thought tetrahedral, right? Okay? Not a tricky question, right? sp3 is tetrahedral, right? Why is it tetrahedral? Because that's the best way for 4 regions to spread out. Okay? sp3 basically means tetrahedral. This is nature. Tie 4 balloons together when you get home. They'll adopt a tetrahedral arrangement. That's nature. Okay? For various reasons. How do we get that? How do we get 4 identical bonds? Well, it hybridizes. All these mixed. Let's put all these in a blender. Okay? I'll go this way. And mix That's a three-letter word, meaning hybridize them. Blend them up, okay? 4 scoops in the blender. Let's put an S in the blender and 3 P's in the blender. Now we're going to scoop out 4 identical orbitals. And we're going to scoop them out, and it's going to look like this. 4 new orbitals. Just like mixing chocolate and vanilla ice cream, and you pull out. Or we'll do paint. Let's mix white and red paint. After you mix it up, it's going to be what? Pink. Okay? No longer red and white. We no longer have those originals. We mixed them up and we made these. They're all identical. They're called hybrid orbitals. Okay? 4 hybrid. What are we going to name these hybrids? They're named sp3 hybrids. And that's just simply what went in the blender? An S and 3 P's. And so we call this 4 sp3 hybrids. Now, how many valence electrons for carbon? Well, those are the arrows. And we fill them just like we would fill ground state, one at a time until, before you start pairing, what is that? Hall principle or something? Hund's rule? One of those. We do that. Now we can start bringing in the electrons from the other guys. Let's bring in an H and its electron and make a bond. Let's bring in another H with its electron and make a bond. Bring in another H with its electron. And now we can make 4 identical bonds to 4 H's or to 4 chlorines. Or it could be 1 to an H, 1 to a chlorine, 1 to a bromine, and 1 to maybe another carbon. It doesn't have to be the same thing. But it's 4 identical. It's 4 bonds made with hybrids. In this case, because they're all H's, they're identical. But this is also tetrahedral arrangement. That is, if we draw a carbon, how do we draw a tetrahedral? How are these things arranged? We have, so this is how I would say tetrahedral. 2 in the plane, like this. And 1 forward. 1 forward drawn bolded here, as if it's coming forward, and as it gets closer to you, it gets bigger. Right? 1 forward, and then 1 back. Now, I'm tempted to go here. It's really going to look more like that. And as it goes away from you, it's getting smaller. Yeah? You've drawn tetrahedrals before. Did you draw tetrahedrals in Gym Chem? Okay. Now this is the orbitals. Before we get there, what do these orbitals look like? Now this is in terms of energy, right? Don't you usually draw some to show this is energy? And the 2p is higher energy than the 2s, yeah? Same thing here. But look where I put the hybrids. The hybrids fall in energy between the p and the s. Why is that?
Because there's more P. There's more P character.
Because it's a mixture of these, just like pink falls in between red and white on a continuum. Okay? Well, let me ask you, is the energy of these hybrids closer to the P's, the original P's, or the original S?
P.
Why is it closer to the P's?
Stronger energy.
Why is that energy closer to the P's?
There's more P character.
Because 3 P's went into the blender. Only 1 S. So the hybrids are going to look more like the P's. If you put 1 pint of, 3 pints of red and 1 pint of white, you're going to get a hot pink. But if you put 3 pints of white and only 1 pint of red, it's going to be more of a softer pink, right? It just comes from that. That's the same thing here. Okay? So the energy here, all right? What do they look like, though? Well, we know this was a volleyball, and that's a dumbbell shape, yeah? It's a little bit hard to draw the hybrids, SB3. How about an S? Let me try to draw an SP. We're not doing that yet, but an S is like this. And it has some phase, we'll denote there. And the P, if we sort of mash it in here with it, we call the phase this like that, because the P orbital has opposite phase on it, okay? Over here, this plus is interacting with the plus here, and it enforces. But over here, it's the opposite phase. You got a plus phase and an opposite phase, and that's counter or destructive. Okay? And so when this hybridizes, you end up with. Now, what does this over here become? It's a mixture of the elongated and the rounded, and it's going to end up looking something like maybe like this. Okay. Just these two, the roundedness and the long. Okay. It's not going to be perfect. On this side, though, what is it going to look like? Remember, it's destructive, it's canceling each other out. And it ends up looking something like that. It's not complete cancellation. Constructive interaction over here leads to something destructive over here. Okay? And this would be an SP, kind of what like an SP orbital looks like coming from. Now, I'm sort of talking as if these are sort of meshing together, blending things up, okay? In actuality, this is a lot of math, okay? A lot of math here, higher level math, of combining these orbitals. Because an orbital is largely mathematically defined and constructed, okay? A lot of math here we're not going to go into. I'm talking more basic approach, okay? Does that make sense? Much harder to draw an SP3 because I'd have to draw 3 P's mixing with this one S. Okay. On the very back page of the handout, we'll see them. Okay. All right. We'll see. The important thing is compared to. How does this compare to maybe an SP3? Relative comparison. All right. Back over here. 4 identical hybrids spread out in tetrahedral. Let's put I drew this here first, but let's make this an orbital. Okay? We're like the hybrid. The hybrid is here. And then that back lobe, that's called the back lobe there. Okay? Back lobe is there. Okay, we can draw it here. But often it's not drawn because it gets cumbersome with your drawings. The back lobe is always there. During test 3, I may refer to the back lobe. Okay? So I'm not going to draw any hybrid's going to have a little back lobe there that comes over this side. We can do the orbitals. There are the 4 orbitals arranged around the carbon in a tetrahedral manner. And this is supposed to be sort of like this, one straight up on the board in the plane, one that way on the board. You see, if the board was here, those 2 would be on the board. Okay? And then this one, that's the board. This one's coming towards you. Okay? It's not going to be perfect. Then you also got one coming back that I'm holding in my hand. Okay? See tetrahedral? It's always 2 in the plane, right there. 2 in the plane, that's the plane. One that way, one this way. All right? Now, that's an orbital. Now sometimes you may see this and this wasn't drawn. To me, it's easier to draw the lines first and then put it, but, okay? It helps you just draw things. Okay, so what is this orbital interacting with? By the way, this is sp3, right? These are all sp3s. 4 sp3s, tetrahedral. What is this interacting with? What type of orbital? The H has 1 electron, but what type of orbital is it there?
S.
Remember? It's the S. And what's the shape of the 1s for the H? Okay, like this. And so this is the H. We can put an H on its back. Really, there's no H written on the atom. What do we have? Right here's where the magic takes place. We have 1 electron from carbon, 1 electron from H. This is a 1s orbital from the H. The 1s is interacting with the hybrid sp3 orbital to make the magical 2-electron covalent bond, which comes from interacting of 2 orbitals. But again, that book is way thick. All right? So are we looking a little bit closer at the bond here? So just repeat this 3 times, right? Can I just do that to just take, instead of writing it down then, let's just repeat it 3 times. Make sense? Tetrahedral? Now this implies that, hey, we can say that this is just H's here. 1 H here, this is 1 carbon. And that's implied to be a bond, but we have to know more details of how that bond is here. This is a different view. It gets us ultimately. Okay. The important thing about what type of bond did we make here?
Sigma.
This is a sigma bond, which is what? What is a sigma bond? Well, it's typically a single bond, but a sigma bond is a bond that is made by the orbitals interacting head to head. What's another way to interact? We'll see in a minute. Head to head. Okay? I can bond these markers together, or you can say end to end, or head to head. Either way, bam! I just made a sigma bond for the markers. What's the other way? Anybody know?
Tail.
All together.
Next to each other. Tail.
Side to side. What type of bond is that? Pi bond. Okay? We'll do that in a minute. But right now, sigma bond is head to head. And the important thing about a sigma bond is it can rotate. Now, this has a little something in it that won't let it rotate. Okay? It makes a noise. See, I can rotate that, it still stay connected. No, atoms don't make noises when they rotate, I don't think. Maybe they do. Sigma bonds can rotate. Rotates, rotatable. Okay. Head-to-head overlap. What else can we say about this? So this is a tetrahedral carbon. Comes from this type of hybridization. It's not a bond. Why does it do this? Well, it's largely driven by the electron wanting to repel and adapt to tetrahedral nature. But it's also largely theory. Why did this theory have to be developed? Why does it work? There's many questions we could ask, but we'd be here till next week, and we've got a lot more to cover because the test is next week. Okay? So we have to sort of end the discussion at some point. But it's theory. It's a lot of theory. It's a lot of math. All right? Let's move on. And as we move on, maybe more questions will come up because as we start comparing. Let's look at ethene. Ethene. Sounds like a 2-carbon alkene. Ethene. Does this sound like what you talked about in Gen Chem? You did hybridization and bonding in Gen Chem? Yay? Yes. Anything new here? Okay, ethane's going to have a carbon-carbon double bond, and in order to do that, we need two carbons. One DUS, correct? Ethene. Slang name is ethylene. Okay. This is going to be an example of sp2. And both carbons are identical. So everything we say about this one, it goes for the other one over there as well. How many regions around this carbon? Either one? 3. Single bond, single bond. A double bond is one region. Okay? 3. How are 3 balloons going to spread out best? Tie them together, they're going to Trigonal planar. Do it. Get some balloons, tie them together at the tie point. You'll have an instant trigonal planar. If 2 are like that and one's sticking up, let me know. No, the other one's going to be like this. And it'll be trigonal planar. Okay? Trigonal planar. By the way, we didn't say what are the bond angles around each of the bonds in that thing back over there. 109.5, right? That's the bond angles in a tetrahedral. That's the standard bond angle. It can deviate from that. Like if you have a lone pair, ammonia, the NH bonds are actually not as large of an angle. All right? But in general, 109.5 is the starting point, yeah? This is trigonal planar. And the bond angles here are, if I drummed this one a little bit more precisely, I reckon. Is that right? What is this bond angle here? 120, right? Right? And what is this? 120, correct? And what is this? 120. And you get a total of 360 around that plane, right? Okay, that's trigonal planar. How do we get to trigonal planar? Okay. The first question you ask is how many electron regions or domains? The answer is 3. And because 3, we need 3 domains. That means we need 3 hybrids. With methane, we needed 4 domains. That means we needed 4 hybrids, and we had 4. But we only need 3 hybrids here. So how many scoops you want to put into the blender? Because, importantly, if you put 4 in the blender, you get 4 hybrids out. If you put 12 in the blender, you get 12 hybrids out. How many we want to put in the blender this time? We only put 3 in the blender. We're only going to put this one, so we're going to blend just 3. Okay? And I know I'm kind of reusing this up here, where you may want to rewrite it or whatnot. You also have the video, right? 3 in the blender, that means we're going to get 3 out. Are these going to be higher in energy or lower in energy compared to the sp3s?
Lower.
Why lower?
Because there's less P character.
Because there's less P character. Or what we'll say is more S character. sp3, what percent S is this? 25% S. We're going to do sp2 here, and this is going to be what percent?
30.
Yes. More S character. The hybrid's going to look more and more like S. Thus, it's going to be an S that's more lower in energy, more stable. So these are going to be lower energy, more stable. Now, I'm not showing them both up here, so it's going to be hard to tell. We'll go back and review that. But we're going to put 3 in, we pull 3 out. And this is 3, what do you want to call these? sp2 hybrids. We just name them according to what went into the blender. one S and two P's. But importantly, what is left over that never went into the blender? Yes. P orbital here, right? It never was hybridized. How many p orbitals did we have in the previous example, sp3, after we hybridized? We had 0 because all original went into the blender. Okay? P orbital. How many valence electrons does carbon have? We could do 1, 2, 3, and put another one here. But it's actually bonds like this. There's your 4. And then we make bond to H. Instead of doing X's, because this carbon is bonded to both H and the carbon, I want to distinguish between H and carbon. Instead of doing X's, I'm just going to draw the H. That's an electron from the H, an electron from the H, an electron from... We're making a double bond to carbon. We need 2 bonds. It's here and here. And that's your double bond to carbon. Now, sigma bonds are always made with hybrids. How many sigma bonds did we make? 3. Okay. Let's draw the hybrids here. Carbon. Okay. Let's draw the hybrids. What type of arrangement are they? I said that right. Trigonal planar. Does that look trigonal planar? Everything's in the plane. Nothing's coming out. Nothing's going back. All right. Okay. But this is an orbital. That's an orbital. That's an orbital. That's supposed to be 3 orbitals in a trigonal planar arrangement. What is this orbital interacting with? That's sp2, sp2, sp2. What is this interacting with?
H.
Well, the H. And the remainder of that's just like previously. I'm not going to draw any electrons. One electron, okay? Just like previous. This interacting with H, 1s, right? Sigma bond to H, sigma bond to H. Overlap of the sp2 with the 1s. Or we can just say s. What is this orbital interacting with? You got identical carbon over here. That is also the same thing, trigonal planar. Boom. Is that what trigonal planar? Hybrid. 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 sp2, sp2, sp2. There's your 3 hybrids for the other carbon. But what's this? That's 2 orbitals interacting head to head. What do you call that?
Sigma.
There's your carbon-carbon sigma bond. That was bonded to the H. That was bonded to the H. Both of those carbons are trigonal planar. All those are sigma bonds up there. This sigma bond comes from sp2, sp2 interaction. Carbon using hybrid orbitals. What else is left here? What else is on this carbon? We drew the 3 hybrids. What else is there? P orbital. How is it positioned compared to the hybrids? I know the shape of a P, but how is it positioned compared to that? If these 3 are flat on the board, okay? If this is like this, flat on the board like that, how's the P orbital? It's on that carbon, but how is it?
And the other.
Is it straight up?
Yeah.
No. It'll be like this. It's perpendicular to that plane. Right? Now if this plane was like that, then the p orbital would be straight up. Now when I say straight up, it's also just half straight down. Okay, I can't split my pen, but it's half up, half down. The dumbbell is here and here. But if it's on the board, it's coming out at you. See, but I can't draw it out at you. There's no board space out here. See, if we envision this going back, that's why some better 3D pictures, which I think are in the handout. But, so, I'm just going to have to draw it like this. And I'm going to make it sort of skinnier and longer to make it different from the hybrids. It's P. This one also has a P because it's identical. And this carbon has one valence electron there. That's the arrow up there. But the other carbon has one too, and I noted it as the C. One electron from each carbon here. They're interacting. Well, they're in p orbitals. The electrons here. How do these guys interact? Not head to head, but can these interact side to side?
Yes.
The way I drew it looks like it's kind of difficult, like they're way apart. Well, in real life, they may be fatter than I drew it, they may be closer than I drew it. There's enough side-to-side interaction that it's a second bond. Okay? I denoted it here because there's electron density both above. Again, if the hybrids are like this, you got half the p orbital up and it's interacting with the other one. But you also have half down, right? Side-to-side overlap. Right? Are these overlapping? You gotta, okay, there's volume here. There's some interaction. It sounds like we're struggling to say there's overlap there. Well, yes. A pi bond is weaker than a sigma. You might think that side to side would allow for more overlap. But it doesn't. I know that pi bond is weaker. Stronger is the head to head. So, what do we have between the two carbons? First of all, that's called a pi bond, right? Between two carbons, sigma bond and pi bond, we call that a double bond. Double bond. Is it all looking right here? Looking good? The important thing about the pi bond is it restricts rotation. Restricts rotation. I don't have large models for double bonds. Here's a carbon-carbon double bond with four things. That's ethylene there. We call it the H's. Okay, double bond. If the sigma framework is there, sigma is the sigma hybrid orbitals. I call sigma framework. P orbitals would be orthogonal to that. They're there. But these carbons can't rotate. Okay, if I put another carbon bonded here, and that's just a single bond, well, that can rotate. Okay? And so this blue, compared to this up black here, it can rotate around. Now it's opposite the one or to the side of it. We'll be looking at that. All right? Sigma bonds can rotate. But if we make a pi bond here between the two, it can no longer rotate. Because if they're here and you try to rotate this, spin it, you just broke the bond. Because you have to have full side-to-side interaction. And you broke the bond. So the bonding keeps it from rotating. Now, enough energy, you can do it, you can destroy the molecule and break the bond. But usually, it's just not going to rotate. And so things are fixed, and you can't do this. All right, we'll be talking about that more. Pi bond restricts rotation. So this is a P, right? How many pi electrons in this molecule?
2.
One.
Well, pi electron is an electron in a p orbital. How many electrons in p orbitals here?
2.
Right? Got one electron in here, one electron there. We made a pi bond. How do you make a bond? Interaction of one electron here, interaction. Make a bond, right? So an electron, usually you might call it an orbital, but an orbital is an electron. That's just a description of the electron. Two orbitals interacting means two electrons interacting. Okay? Two, made pi bond. Look over there. I mean, how many electrons in the p orbital?
2.
Got one from each carbon. Okay? Questions next. Ethine. 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 Making sense? What type of questions have come up? Okay, ethine. You have to have two carbons to have a carbon-carbon triple bond. Ethine. These two carbons are going to illustrate sp. Both identical. How many electron domains around this carbon?
2.
Two. Single bond, triple bond. Two regions, domains. How are these best spread out? If I tie two balloons together, they're going to be... All right? You got to try it. If you tie two balloons together and one's sticking straight up and the other one's like that, call me. Okay. It ain't going to be like that. They're going to be like this. Okay? Linear. SP. Linear. That is, what's this bond angle here? The HCC angle 180 degrees. Is that right? How do we get this? We need two regions here. How many hybrids do we need? 2. You need two hybrids. We're just going to put one S and one P into Blender. Mix them up. Okay. You can add in some daiquiri mix if you want. And we're going to get out two SP hybrids. SP, what percent S? 50% S. Which hybrid is longer? We didn't draw the exact shapes of these. We know what an S looks like, we know what a P looks like. Which of these is longer?
SP3.
SP3, why is it longer?
Because it's got more.
It looks more like a P, which is longer. Which one's fatter and rounder? This one, because it looks more like an S. It's got 50% S. Which orbital is going to be a more stable place for an electron? SP, because it's more S character. And S is lower in energy and more stable than P. It all comes from 9% S character. Okay? So I didn't position these exactly because we only had one at a time, but the other hybrids were all higher in energy. More S character getting lower down. What if it was 100% S character? It would be the same, it'd be here, just like that. Okay? What's left over? What did not go into the blender?
Those 2 p orbitals.
2p orbitals. Okay, we got a carbon. Linear. Okay, here's a hybrid. Here's a hybrid. That looks like a P. Almost, but it's really 2 hybrids. This has a back lobe that I didn't draw. That has a back lobe I didn't draw. They're just positioned linear. This is an SP. That's an SP. What is this interacting with? H, magical 2-electron bond. What is this interacting with? Identical carbon. It also has 2 hybrids. Okay? 1 electron from there, 1 electron from there, magical there. What type of bond did we just make? Sigma bond, right? Head-to-head overlap of 2 hybrids. This carbon is bonded to a H over there. What else is on each carbon? 2 p orbitals. One of them is in the plane, along with this. That's interacting side to side to make pi bond. Don't think it's 2 pi bonds. That's just the interaction above and below the plane. Or if you consider that the plane, right? Okay, that's 1 pi bond we just made. Side-to-side interaction of 2 different p orbitals there. What else is on this carbon? A second p orbital. Well, the second one is coming out at you like this. And going back, it's this way. Okay? One of them is straight up. The other one is like that. They're orthogonal, perpendicular. Or however you want to consider it. Okay? The other one is very difficult for me to draw. I'm just going to have to put it up there and we're going to have to look at a better picture somewhere. But it's going straight back. How about if we just do it like this? And then somehow say that they're interacting. Let's get them interacting somehow. Okay? Second pi bond. How many bonds between these carbons? 3, triple bond. One's a sigma, and then how many pi bonds? 2. Triple bond total. What do we have over here? If we graph our hybridization, we have, let me do it this way. Let's do it sort of backwards at the end. Look here, what type of bonds do you see? That's what we're graphing one of the carbons. What type of bonds do you see that carbon making? Sigma bond to H, sigma bond to carbon. Okay? Sigma bond to H, sigma bond to carbon. You make sigma bonds using hybrids. What else do you see here? This carbon is also making 2 pi bonds to carbon. We'll show you 2 pi bonds to carbon. What type of orbitals do you make pi bonds with? P. Pi bond to carbon, pi bond to carbon. There's your triple bond. So you can do it sort of in reverse that way. Just based on what you see. What you see sort of, this is what you see, right? I mean, look at this. Right? Right? That's pretty good. Pretty good drawing on that. That's one of my better ones over the many years. All right? It just looked nice. What type of questions did we have? How many pi electrons in this compound? 4. Well, you can see it here. There's 4. Okay? So 2 pi bonds. Each bond is 2 electrons, right? Let's see. We have which handout? Functional groups, DUS. There you go. There's some beautiful artwork there. There are your three hybrids. Compare relative to each other. Does that make sense? sp3 is longer. Back to this handout. We said this over there on the right, correct? The sp gets shorter and rounder as it becomes more s characters. Which hybrid is going to make the longer bond? sp3. The longer orbital. Which hybrid is going to make the stronger bond? sp. A couple of reasons I reckon. One, it's shorter. Shorter can make stronger bonds. But I would probably say instead, which orbital is lower in energy? sp, more s characters. The lower energy orbitals typically make stronger bonds. Okay? Yeah. No matter what it's bonding to. These may be bonded to, in this case, the sp is bonded to the s of the h. But this is a stronger CH bond than the previous examples. Because here the carbon is using an sp, correct? That's a stronger bond than an sp3s. The s is the same. A more stable orbital and shorter orbital is going to make a stronger bond. It all comes from percent s characters. Now we can understand things in this table. Largely also review. Ethane, both carbons are sp3. My example, I just did methane because we only need one carbon. Both of those carbons are sp3, correct? 4 regions, you expect sp3, yeah? Bond angles, all the bond angles here are 1 and 9.5. Length of the carbon-carbon bond, 1.54 angstroms. We'll compare that to other numbers. Typical bond length is about an angstrom. Somewhere in there. Strength of the bond, kcal per mole is the one I would probably focus on. Strength of what bond? Carbon-carbon bond. Got to be careful here. I don't like they call it a bond. That's obviously just a bond, but this is 2 bonds? So are they referring to just one of the two, or what? That's what I don't know. Here's what they're referring to. They're referring to the entire bonding between the carbons. Which is stronger, single, double, or triple? You better say triple. Right? And indeed, it's stronger. Okay? This is double bond. Why is it not double 90? Why is it not 180?
Because of pi bonds.
Because this is a sigma and a pi, and the pi is not as strong as a sigma. This is apparently just a sigma bond. Because that's all there is between the two carbons. Everybody agree? What's the strength of the sigma bond down here, do you propose? Anybody? You want to say it's also 90? Is the sigma bond that's here more than 90 or less? This is a bond strength. This is the amount of energy required to break the bond. The more energy required, the stronger the bond. Is the sigma bond here stronger or weaker? Stronger, right? Why is it stronger? No, we're just focusing on the sigma bond. Why is the sigma bond stronger here than above? More energy. That's what I'm saying. Why is it lower energy? Or why is it stronger bond?
A shorter one.
Closer together.
Uh-huh.
Even more.
Okay, this is sp3, sp3. This is sp2, sp2. Which one's going to make a stronger sigma bond? Right? Stronger sigma bond. It's using lower energy orbitals. Okay? Isn't that what we said above? Okay? Stronger sigma bond. The sigma bond down here, maybe it's 100. It should be stronger than the above sigma bond. And then maybe the pi bond is 74. I don't know, but what I'm trying to get you to see is the sigma bonds are not the same in these two compounds. Have to look at what type of orbitals are being used. Okay, sigma bond down here. What do you think it might be? Just some random number. Let's say 110 kcal per mole. Okay, and then the rest would be 2 pi bonds would perhaps equal to add up to 231. Okay? Because the sigma bond down here is what? SP to SP hybrids interacting. Yeah.
To sum it up, would you say that a sigma bond is stronger as the hybridization shortens? Like to sum that idea up?
Yeah, and that's what we said up here. Which is going to make a stronger bond? And I said 2 reasons. Shorter bonds are stronger. But also the SP is just a more stable orbital because it's got more S characters. Strength of that. Length of the CH bond, not a huge difference here, but the trend should be clear. This is longer. Why? Because sp3s. This down here is what? SPS, which is going to make a longer bond. sp3s, because the sp3 is a longer orbital than the sp. Everything is here, and then the bond strength, it's all there. Basically, length of the hybrids dictate bond length, but also stability of the hybrids dictate bond strength. More stable the orbital, stronger bond it's going to make. Or you can say shorter the orbital, more stronger bond it's going to make. I don't know if that's always the case. Basically, I look at it as if the electrons are in a more stable orbital, they're going to make stronger bonds. But you're putting energy in to break the bond. If the electrons already exist at a higher energy, it's going to be easier to just break it. Okay, let's take a short 2-minute break. If you need to run to the restroom or something. Stretch. Let me erase here and see where we want to begin.
You know it's not the first time she did that,
Do you
right?
have lapis?
Yeah, you have to have your lab coat, your glasses, and that's pretty much it. You have to have your lab fingerprint, so everything, to like check off your list and stuff. I mean, you don't have to have it for this lab, but the next lab you have to have it. It's not the end of the world.
We can look at the one below there, question down there. Yes? How many rings do you got there? 5? Looks like 13, 5 months. 18?
Yeah, okay, I just wanted to make sure I was right, I counted.
Smallest ring you can have is 3. Okay, you can have 2 members.
Yeah,
There
it's
must
not
be a
right.
line.
Yeah.
And then, oh, we went over my other question.
Top one is singular,
Yes.
18 DUS.
Yes.
What was the other question? Formula?
Well, my other question was gonna be about, like, you kept asking, the lone pair in the nitrogen, like, trying to figure out which orbital.
Okay, we're gonna do that, some of that right here.
No, I just asked him if my gene is correct. Because I got 18, and I just want to make sure he counted that ring, cyclopropane, the cyclopropane.
Yeah.
Yeah, I just want to make sure that was right.
What was the name of that?
Cyclopropane.
Cyclo group.
I mean, but yeah, I mean, you know.
I'm just testing.
Yeah,
Recognize that, right? You know it was cyclopropane?
well, when I came in here, I said propane, she corrected me on
Okay.
cyclopropane.
I figured that. So you knew it was cyclopropane. That tells me rings will say cyclopropane. Cyclopropane. Unless it's a common name. I mean, benzene is almost a common name. Benzene is not a saturated hydrocarbon. Saturated rings we say cyclohexane or butane.
It's all, so you correct me, so when I was learning it on your sheet, it was like you were using them interchangeably, benzene, aromatic, but you were saying.
Benzene is an aromatic.
But,
Benzene is aromatic, but not all aromatics are benzene.
yeah.
Many are type aromatic rings.
Also, it's
Benzene
like,
is just the granddaddy of them all.
also, it's like,
Ethene is a 2-carbon alkene. Ethene is alkenes, but not all alkenes are ethene.
I love it.
Some are butenes. Some are hexenes. Alkene is a generic term.
Yeah, they're just hating.
Butene is a specific 4-carbon alkene.
Okay.
You can also have isomer butene. Okay, guys. There's a structure below, Prozac. Which ranks bonds along with shortest? Which bond is longest? Throughout my handouts, you'll see questions like this. Please always attempt them and know that they're coming. Okay? Which one's longest?
A.
Why is A longest?
Because it's SP3.
sp3, sp3. Both those carbons are sp3 using sp3 hybrids. A is longer or greater than what?
B.
Yes, B, and that's longer than C. Okay? What orbitals are being used to make B?
SP2, SP3.
S- sp3 The A is sp3, sp3, and the C is
SB2, SB2.
sp2, sp2. All right. How about this? Let's look at things other than carbon. How about the nitrogen? What's the hybridization of the nitrogen? And can you graph the hybridization? We graph the others sort of in the middle here. Okay. There's a lone pair there, right? Okay, we gotta know that. How many electron domains around that atom? Around that nitrogen? It's the same questions. The fact that there's an N doesn't matter. It's the same old questions. 4 regions. So what hybridization do you expect?
SB3.
sp3. So graph the hybridization. What type of bonds do you see there? sp3. That would be 4 identical hybrids, right? Any p orbital here? No, we put them all in blender. No p orbital. What type of bonds do you see this nitrogen making? Sigma bond to carbon, sigma bond to carbon, sigma bond to H. What type of orbital is the lone pair in? Where's the lone pair? Here's a hint. There's only one place it can be. Right there, right? Where's it go? I mean, it goes right there. Where else are you going to put it? Lone pair. Okay, LP. There you go. There's your hybridization graphing for that nitrogen. 3 sigma bonds using hybrids. You see 3 sigma bonds, right? That's condensed. There's a bond there. Single bonds or sigma bonds. I'm willing to do it almost all the time, but let's say 99% of the time. Exceptions are everything. I can't think of an exception right now. For us, single bonds are always sigma bonds. Sigma bonds are made using hybrids. We have the hybrids. All these electrons around that nitrogen are spread out in a tetrahedral manner. Bond angles typically 109.5. The carbon-nitrogen-carbon bond angle may be less than 109.5 because the lone pair tends to push things together. You talked about Benzinkian, lone pair repulsion a little bit. I'm not going to get into any precise bond angles. There you go. LP in sp3. Graphing the hybridization. I'm probably the only instructor who really focuses on graphing the hybridization like this. Why? Because I think it becomes a no-brainer to answering all the questions. All right? If you want my advice, learn how to graph hybridization, and that's it. All right? Let's look at the drug sheet in the syllabus. Let's find another compound. Or maybe on the DQ page. How about that? Got that handy? How about the singular nitrogen? Okay? If you're on another page, just make a note. Okay, circle this nitrogen we're dealing here, right? Lone pair, right? Question, what type of orbital is that lone pair in? Is the answer easy because there's only one choice, or do you have more than one choice? Nitrogen is, what hybridization is that nitrogen?
SB2.
How many electron regions around it?
3.
3 regions, typically sp2. Okay? sp2. sp2. That looks like what? 3 hybrids and a P? Remember, the question is, what type of orbital is the lone pair in? Well, graphing hybridization. What type of bonds do you see that nitrogen making? How many sigma bonds is it making?
2.
How many sigma bonds? I said 1. Who said 1? Why 1?
Is it only the rest is a lone pair and the other one has a pi bond?
Yeah, a double bond is what?
Sigma.
Sigma and a pi. I see two sigma bonds. I see sigma bond to this carbon and a sigma bond to that carbon. Sigma bond to carbon, sigma bond to carbon. What else? What other type of bond do you see? Pi bond to carbon, right? And what is this all together? There's a double bond to carbon on the right side, single bond. Here's your question. What type of orbital is the lone pair in? Lone pair is right here. Uh-huh. And if we do that, we know that these three are spread out in what type of geometry? Trigonal planar. Does that look trigonal planar? Okay. That's a carbon. That's a carbon. Carbon, carbon. What's in this region here? It's a lone pair. That's an orbital in that region. That's an sp2 orbital, but that orbital just contains a lone pair in that region. It's one of those regions. Now, what else is on this nitrogen that I'm not shown yet? I'll just make that a bonus. Also a p orbital. But that p orbital is interacting with what? I'll try to draw it on there. This carbon over here has a p orbital, and that's the additional pi bond.